Welcome to the second lecture in quantum field theory. Now this time we will begin discussing the Klein Paradox. The Klein Paradox is very interesting because it will show us some further problems with the Klein-Gordon equation, but also give us some interesting hints as to where this entire thing is going. So what we will do here is we will consider this situation. We have some particle that is incident on this barrier. Okay, so there is no potential here, and then there is an electrostatic potential. Okay, so it's not just any potential, it is an electrostatic potential in this region 2, which starts at z equals 0. So let's study this situation. Let's find the transmission coefficient, the reflection coefficient, and the way we have done it in the past. So to do that, we will begin by writing down our equation. Okay, so we know that we have the Klein-Gordon equation, m squared, acting on our wave function. Now this is going to be a function of z and of time, actually, equal to 0. And of course, let's keep in mind that the D'Alembertian here, this square is called the D'Alembertian. This is simply d mu. Okay, so what we now want to do is keep in mind that now we're going to be dealing with an electrostatic potential, which means, of course, that we need to take into account what we have learned in courses in electromagnetic theory. And in particular, we need to take into account that when we are in the presence of this electric field, what we will have is that our derivative here, right, because of the change in this situation where we have this new potential, will go to d mu plus I e a mu, right? And similarly, the mu covariant will go to d mu plus I e a mu. Okay, this is called minimal coupling. So if you have not seen before, we will go a little bit more into it. The whole point here is to make this gauge invariant. Now you may not know what gauge invariance is. Again, don't worry, we will go into all of these situations step by step. This is not the main purpose of this lecture. And we will have other lectures where we'll go into detail there. So if you have not heard about this, don't get too worried. Just take my word if you have never seen it, and we will go into detail in other lectures once we have a bit more time. Okay, and by the way, this is supposed to be an arrow. Okay, so what we now want to do is plug this in, but considering what a mu is, right? This a mu, in case you don't know what it is, that a mu is a 4 vector that we define in terms of the potential vector from electromagnetic theory. So we had two interesting quantities in electromagnetic theory. We had the potential scalar, this is the scalar, and we had the potential vector A. And we can build a 4 vector by defining this as a mu, and this is going to be phi comma A. So this is going to be our 4 vector that will show up all the time when we deal with anything that is remotely electromagnetic. Okay, so this is a very important 4 vector. Of course, the contravariant vector would be phi comma minus A. So since our potential is only electrostatic, there is no magnetic field, nothing is changing, it's all constant. That means that our vector A that is associated to magnetic fields is going to be 0. Okay, so a mu and a mu will be the same. So they will simply be phi comma 0, right? Since the part that usually changes with minus sign is 0, so it makes no difference. So that's going to be our vector. So what we now want to do is plug these things that basically contain the change that we made. They basically tell the equation the physical situation that we're in, right? They're telling the fact that we now have this potential. So let's plug it in. So d mu contravariant now goes to d mu plus I e a mu. And then we have d mu down here plus I e a mu. And then, well, we still have m squared, all of this acting on phi. I'm going to write it as t comma z. I did it the other way around before, but it doesn't really matter. Okay, now let's multiply through, not really doing anything else. So we get d mu. Now I wouldn't write this as the D'Alembertian, because we want to apply the derivative soon. So I think it's a bit more intuitive like this, but it doesn't make any difference. Then we multiply here. We have IE a mu d mu. Then we have the next term. So we have that times that times that, then plus d mu IE a mu. And then we have minus e squared a mu a mu. I wrote it down in the, I commuted them basically, because we know that it is the same a mu up here times this, or this times that. It's the same. The order doesn't matter there. I didn't do it on purpose. I just noticed that I did it the other way around, and well, it doesn't matter, so I'll just keep it like this. Plus m squared acting on phi t comma z is equal to 0. We do have a few different phi's though, so actually maybe let's call this phi right there phi 0. Okay, so this is phi 0, and the wave function is simply phi. Okay, now what do we do here? Well, let's now define some of the things that we have, right? This is the equation overall, but we know what a mu is. A mu is simply phi comma 0, right? We have it right there. So what is a mu? A mu, right? So what is a mu? A mu, which is of course the same as a mu. A mu. So that is going to be the first term squared, which is phi 0 squared, minus the other terms. But the other terms are 0, so it doesn't matter. Okay, so that is what we can plug in here. So this thing that right there is phi 0 squared. Then we have an a mu here. Now this is going to be phi 0 comma 0. Then we have these derivatives, which we know this is covariant. So this means time derivative. I'm doing it in a very compact notation because I don't want to have to erase anything, right? So sorry, it is positive here, not negative. Sorry, there we go. And then we have another one of those. So this is time derivative and the space derivative. And then we have these two here. I will delete it there. And this will be, now I'll just take the space to do it. So ddt and minus the gradient and ddt, comma, and then we get plus the gradient. Okay, so that's everything that we have in here. And yes, okay. So now there isn't really that much more we can simplify. There are a few more things. Oh, I forgot about this a mu, by the way. Whoops. Well, this is phi 0 comma 0. Okay, we are a little bit short on space there. Okay, so now what we want to do is, well, I will keep this here the same. So actually, let me just copy it because I don't want to have to write it again. So I will keep it as it is. But now, take a look at the other term. So here we have plus IE, and then we have phi 0 comma 0. So if we want to multiply these two together, the spatial part will not matter, because if we take the derivative of anything and we then multiply by 0, it's going to be 0. So in both of these terms, in both of those, there will not be any space part, right? It will go to 0. So that means that here, when we multiply through, we will simply get phi 0 times the time derivative, which I will now write explicitly as ddt because I have enough room. And then we have here the time derivative of IE phi 0. But phi 0 is a constant, so we can just write it in front, and we end up with the exact same thing as here. So we can simply write this as 2 times that. Okay? So now we have that and that. And finally, well, we have minus e squared phi 0 squared plus m squared. And all of this multiplying our wave function. So we can't really go any further now without specifying a wave function, right? And by the way, I guess we didn't really have to write this like this. You could have kept this as d mu. This didn't really make it any simpler, so if that looks ugly, you can just stick to this notation or also just to the D'Alembert for now, because we need some wave function. So taking a look at what's going on here and remembering the solutions that we saw in the last video for the Klein-Gordon equation for, just a single particle, what we can do, I'm thinking where I should write it, maybe here. What we can do is the following. We say, okay, so in region 1, there is no potential. So in region 1, there is no potential. So I expect that my wave function in region 1, which will of course depend on z and t, will be some incident wave function, which will be described by e to the I k, or rather, now instead of k, let's just write it as with the momentum, right? As pz. It's the same. E to the I pz, and this will be incident, right? This will go in that direction, but then we will get a reflected one, right? Some part may reflect from our potential, depending on the exact situation that we encounter. So we have to allow for a wave function that is traveling in the opposite direction and will have some amplitude, right? I'm saying the amplitude of the incident wave is 1 because we will have a 100% probability of finding the particle there once we are, before it even arrives. And then we'll have this a, which will, of course, or should be less than 1. Okay, so there we have the incident wave function, but we still need to multiply by e to the minus I e t, right? The energy will, of course, be conserved, so both of them have the same energy. And then we have, for region 2, there we have that our wave function, z comma t, will be now some other constant, right? Some other coefficient times e to the I p prime, the momentum may change, and in fact will change, times z. Okay, so that is our wave function in region 2. So with those solutions, I'm going to actually move them further down, and we will plug them into this expression right there, right? Into the Klein-Gordon equation, but that we modified for this particular situation. Okay, so if we do that, we need to insert it here. So of course, we'll have two different results. We'll have, actually then maybe let's just write it down here so that it's a bit clearer. So for region 1, right, we'll have two results, one for each region. So in region 1, we have to use this wave function right there. And also, we have to keep in mind that, well, in region 1, there is no potential. So everything, all of these phi 0, phi 0, it all goes to 0, and we just end up in the regular Klein-Gordon equation that we have seen already, right? So this would be 0, this would be 0, and we are back to just the regular Klein-Gordon equation. And that, of course, makes sense, right? If there's no potential, then you don't do those changes. Okay, so what we need to do there, I'm going to do this step by step to make this very clear. So we'll have d mu plus m squared acting on our wave function. What is the wave function? It is e to the minus I e t, and then e to the I p z plus a e to the minus I p z, and this has to be equal to 0. So let's now apply this. Now again, what is this? We can write it now multiplying through what we had before, or just keeping in mind how we multiply these things, right? This is, we are summing over this dot product, and we end up with the first term squared. So we get d dt squared, so d squared dt squared minus, and then we get the second part squared, which will be minus nabla squared. Okay, so we have this, and then of course plus m squared, and then times, well, that same thing that I'm too lazy to write. And now we actually apply this, right? Now we know how to do this. There's nothing new here. So time derivative of this entire thing. So if we apply the time derivative twice, we get minus twice, so it is positive. We get I squared, which gives us a minus. We have e squared, and then everything else is still the same. So, and then times the wave function. I'm just going to write it like this because why would I bother writing it down again? And then we have the spatial derivatives, which of course in this case will only be in one direction, right? It's only going to be in the z direction. So I guess you can write it like this. Now this part may be a little bit confusing, at least it's just regular calculus, but let's not make any mistakes. So let's just do it slowly. So we have, let's see, plus, or rather minus, I guess, minus e to the minus I e t. Why minus? It's that one, just to make sure. And then we have to take the z derivative of that. So the z derivative of this is going to be minus p squared e to the I p z. And then the z derivative of this will be minus p squared a e to the minus I p z. The minus cancelled out there, this one. Okay, and then we of course still have plus m squared times phi. And all of that is equal to 0. I'm going to have to move the camera a little bit. Okay, so here we can factor something that's out. So minus e squared times phi. I will omit now the dependence because I'm lazy. And then we have, here we can factor out minus p squared. And the minuses will cancel out. So we get plus p squared. And everything else is simply phi. So we get phi plus m squared phi is equal to 0. So finally here we can factor out phi. So we factor it out. So all of this times phi. So if we want this to be equal to 0, for either the wave function is 0, in which case we don't have anything going on, which of course we cannot accept because that's boring, or this is 0. So in that case, we have that minus e squared, well, minus e squared plus this has to be 0, which is the same as e squared is equal to p squared plus m squared, which may seem familiar. Right here we retrieve, this is very similar to what we did in the previous video. Here we retrieve the famous plus or minus square root of p squared plus m squared. But here we are going to say, okay, our particle is traveling, so of course it has to have positive energy. So we will only keep the positive energy, right? Which is, right, you see how weird this is, but we will do it for now just to continue studying this. And eventually we will come to deal and understand the negative energies better. Okay, so we dealt with region 1. Now let's go for region 2. So region 2. So I will actually probably just copy this. So in region 2, our wave function is fortunately a little bit simpler. It is bei p prime z. So let's plug it in. So our wave function here is bei p prime z. So that is our wave function. Well, I just noticed I forgot to multiply here by e to the minus I e t. I'll just add a comment later so that you guys don't get confused by that. Okay, so of course here we still need to multiply by e to the minus I e t. Okay, so let's now just multiply through again this thing right there. As we just saw, that is second time derivative minus nabla squared, which is of course simply the second z derivative in this particular case, because we are only dealing with the z direction. So, well, let's now do this. So if we take two time derivatives, we get a minus from the I squared and e squared, just like before. And then we have minus 2 times the z derivative. So we get another minus from this I squared. So we go plus p prime squared. And that would be it. I'm already factoring out the wave function, by the way. I'm going a little bit faster here. So this in principle still multiplies the wave function. This multiplies the wave function. I guess I'll just write it down to make it clear. Then we have plus 2i e phi 0 time derivative, which gives us another I. And so time derivative and a minus sign. So I guess I'll change the sign. So it gives us a minus sign, an I, and an E. And I didn't actually mean to change colors yet. So let's go minus E and still multiplying by phi. And then here, well, none of those change anything. So minus e squared phi 0 squared plus m squared. And of course, times phi. And yeah, and that's it. So this is equal to 0. Again, we can factor out phi, and if we want this entire thing to be 0, either phi is 0, in which case we don't have anything in the second region and we don't have any physics, or everything else is 0. So in that more interesting case, we have that minus e squared plus p prime squared, and then we have plus, right, this I squared will cancel out the minus sign, 2e phi 0 minus e squared phi 0 squared plus m squared is equal to 0. So in this case, what information can we find, right? Because previously we found a relation for the energy. But what can we even find from this? Well, we could solve for the energy, but that would be a little bit boring because we already have something for the energy. So maybe let's go for p prime because we don't really know anything about p prime just yet. Whoops, I deleted this. So let's solve for p prime here. So p prime squared will give us e squared minus 2e phi 0 plus e squared phi 0 squared minus m squared is equal to 0. Okay. So here we can see that p prime is going to be the plus or minus the square root of this. Whoops, I should have included that equal to 0, by the way. Whoopsies. Okay, so p prime is going to be that. The problem is this looks very nasty. So let's try to factor it a little bit to make it look nicer. So this has 3 different terms that are squared. It has e squared, small e phi 0 squared, and m squared. So there's a good chance that this is the product of 2 different polynomials here. One with, well, maybe not a polynomial, but anyways, one of them has a big E phi 0. I mean, both of them have all of these terms, right? E phi 0 and m, but the question is, what are the signs, right? So because this already has a 2, so it really looks like the multiplication of these 2 things. But let's see, what are the signs? This e times this e must give us positive, so both of them should be positive or both negative. Let's just stick to positive for now and see what happens. We also know that m times m will have to give us negative. So either this is positive and this is negative, or the other way around, okay? So let's just keep that in mind. And we also know that this has to be positive. So this term and this term have to have the same sign. Okay, so let's see. We have e squared times minus 2e phi 0, right? So basically e and phi 0, which are here together, and e, which is here. Why am I doing all this? Because that means that when we multiply this with this, we need to get minus e phi 0. So that when we multiply this e phi 0 with this e, we get minus e phi 0, so that when we add them together, we get 2e phi 0. So how can we do it so that we can accomplish that? Well, in that case, both of our energies would have to be positive or have a positive sign, and we would need that this e phi 0 have a minus sign, and we know that the other one also has to have a minus sign, right? They have to have the same sign as we just saw, and also they need to have the same sign for this to happen, right? So this times this needs to be negative, this times this needs to be negative. And well, now the final part, we need the m's to have a different sign. Now it doesn't matter which one is positive and which one is negative because it's the same. You can just flip them around and you get to the same result. Okay, so this is my guess. Now let's multiply through and check. So multiplying through, we get e squared minus e phi 0 minus em. Then we have minus e phi 0 plus e squared phi 0 squared plus em phi 0. And then we have me plus, no, sorry, minus me phi 0 minus m squared. So let's see. This term, me phi 0, cancels out this one. Then we have me, which cancels out this one. And we end up with this is there, right? This and this is that. That is that, and this is that. So yeah, this is indeed correct. So we can have that happily. So we found a nice expression for the momentum, but there is a little bit of an issue because you may see that it can either be positive or negative, which is weird. It is also, it's weird, right? Why can it be positive and negative? This is another issue that arises from the Klein-Gordon situation, from the Klein-Gordon equation. But let's roll with it, right? Let's not think too hard about it for now, and let's just continue. So how do we even know like when to choose positive or negative here? Well, something that we can do is just go back a few steps, right? Just go back here, for example. Let's square this expression, right? Just have a parenthesis here. So p prime squared is e squared minus 2e phi 0 plus e squared phi 0 squared minus m squared. So we want to find some condition for these terms that tell us when to choose, right? So something we can do, since we are working with waves, is see, okay, let's take a look at the group velocity, for example. So the group velocity, we know that, well, this is from other courses, we know that this is simply the partial derivative of the energy with respect to momentum, but in this case, momentum is p prime, so we write like that. So we can take the derivative up there, right? So there, we can take the derivative. So taking the derivative of p prime squared with respect to p prime, we get simply 2p prime. And then deriving this with respect to p prime, we get 2e times whatever dependence e may have on p prime, right? And then we get, that's the chain rule there, minus 2e. And this energy will now simply be dE dp prime. We don't really know exactly how they relate, so let's just keep it open. And none of these things depend on p prime, so they are 0. Okay, now we can divide by 2. So this goes away, this goes away, this goes away. And now we can factor out here this derivative. So we get dE dp prime times e minus e phi 0. So we can see that the e dp prime, which is precisely the group velocity, this is p prime divided by e minus small e phi 0. Now we expect that the transmitted wave will be traveling to the right. So for that to happen, right, for the group velocity to be positive, right, if we want this to be greater than 0, then if p prime is greater than 0, right, we require that e minus e phi 0 also has to be greater than 0. Otherwise, it would turn everything negative. And if p prime were to be negative, then it would require that e minus e phi 0 also were to be negative. Okay, so this gives us a nice condition so we can know when to choose which sign for p prime. Okay, so now we have found these nice relations coming from just putting these expressions for p prime and e in terms of quantities that we may know, like the mass and p, for example. And now we want to continue. So what did we usually do, right? In the end, this may look nasty, but this is still just a scattering problem, right? So what did we do before in this sort of problem? Well, what we did was apply boundary conditions, right? So what would the boundary conditions be? Well, exactly the same as before. So we will apply boundary conditions just like we did to do when we were young. So boundary conditions. Of course, we have continuity of phi. So in that case, we want phi 1 evaluated at z equals 0 to be equal to phi 2 evaluated at z equals 0. So let's do that. So taking a look at the wave function that we have, you may not see it entirely, but you can see it from before. We get e to the IPZ, which will give us 1 at 0, plus a has to be equal to b. And then we have the condition for the continuity of the phi dz evaluated at z equals 0. So let's calculate that. So the derivative at z equals 0. Now note, of course, that the time part cancelled out here. Okay, so that's very important. Both of them have the same time dependence, so it cancels out from both sides of the equation. That's why it didn't show up here. And then we take the derivative here with respect to z. So from phi 1, we have ip times e to the ipz evaluated at 0. So that is 1, so no need to write it down. Minus ipa times the exponent, which will go to 1. And this has to be equal to ip prime times b. Just double checking that the signs are correct. I believe they are. Okay, so now what do we have? Now we plug in, well, now we solve for a and b, right? We have a 2x2 system of equations. So let's, for example, plug in 1 plus a in here. So let's do that. So we get that, well, the i's cancel out everywhere. So we have p minus pa. This is equal to p prime times 1 plus a, which gives us p prime plus p prime a. Okay, so let's combine all of our a's. So we get p minus p prime. This is equal to a factor of p plus p prime. And now we divide to find a. So a is simply going to be p minus p prime divided by p plus p prime. Okay, so that's a very important result. And we can now just plug it in here to find b. So b is going to be p minus p prime, p plus p prime, right? This is a, plus 1. But we can write 1 as p plus p prime divided by p plus p prime so that we can add those two together. And let's see, we get 2p and the p primes cancel out. So p plus p prime. This is another very important result that we will use later to find some more things. Okay, so now we found a and b in terms of the momenta. Now, to find the reflection and transmission coefficient, which is actually what we want to do, we have to keep in mind that the reflection coefficient is the probability current of the reflected wave divided by the probability current of the incident wave, and the transmission coefficient will be the probability current of the transmitted wave divided by the probability current of the incident wave. So we need to find all those quantities. Now, how do we calculate any of those currents? Well, we will have to think back to the equation that we found in the previous video, but it's actually the same that you have already seen in your quantum mechanics courses, which is that the probability current is 2mi times phi conjugate times the nabla phi minus phi nabla phi conjugate. Okay, so we'll have to calculate this for each one of those cases. So let's begin in the incident case. So incident, we know that the wave function, the incident wave function, that is simply e to the I, momentum, sorry, not k, pz. Okay, and of course we'll have to evaluate that at 0, but we'll still have to take the derivative, so let's do that first. And the derivative of this, phi I, with respect to z, right, which is of course going to be the same as this, because we only have one spatial direction here, so this is of course the same as just a z direction, a z derivative, because everything else is 0, okay? So here we take the derivative, we get ip e to the ipz, but we evaluate at 0, and this is 1, and this is also 1. Then we have phi conjugate, which will be e to the minus ipz, and the derivative dz will simply be minus ip times the exponent, which will be 0. The exponential will be 1 because the exponent is 0. And this is 1. Okay, so now we just plug this in, and we get that the incident current is 1 over 2mi times phi conjugate, which is 1, d phi dz, which is ip, minus ip, so plus ip. So the i's cancel out. We get 2p over 2m, or simply p over m. Okay, now I don't have space in that direction. Let's go here. So now let's do the exact same thing, but for the reflected wave. So for the reflected wave, in that case, our wave function for the reflected case is going to be a e to the minus I p z. Now the complex conjugate of the reflected wave will be the conjugate of this. So we get a conjugate e to the I p z, right? Notice that a could be complex because a, where here, depends on pi prime, and pi prime could be imaginary, right? This square root may very well not be positive, so you could end up with something imaginary or complex. So we have to account for every single possibility. So for now, we will just write it as a conjugate. Okay, now we take the derivative. So we get d phi r dz. This is equal to minus ip times a times the same exponent. But again, the exponents go to 1. And then we have the phi r conjugate dz, which will give us ip times a conjugate. And well, then this exponent also goes to 1. All right, now let's plug it in. So we get that j reflected, this will be 1 over 2mi times phi conjugate here, so a conjugate. Then we have the derivative with respect to z, so we have minus ipa minus phi, which is a, and this other derivative, so ipa conjugate. So here the i's cancel out, and we have the exact same thing twice. So we end up with minus, let's see, 2pa conjugate divided by 2m. Now here we do have to make a little bit of a correction, because what I called J reflected, right, the reflected wave, this is going in the minus z direction, which is actually why we have this minus sign here. So just the coefficient itself will be without that negative sign. Okay, so that's a correction because of the fact that what I called J reflected here, right? This is basically going in the minus negative, in the minus z direction, right? Minus z hat. So that's why we ended up taking the minus out of it, so that we end up with just the coefficient itself, right? So that is what we did there. Okay, so now we have this expression for the reflected, the reflected probability current. And now, well, we can still, by the way, simplify the 2's. Now let's plug in the values for a and a conjugate, right? Because we already have them. So we have p over m, and then let's put in the value for a, which is p minus p prime, p plus p prime. So p minus p prime, p plus p prime, this is simply a. And then a conjugate is p minus p prime conjugate, right? P prime could be complex, so we have to consider that possibility. And the same thing, but like that. Okay, so that is the reflected probability current. Now, finally, let's go for the transmitted one. So I'm going to use yellow, I guess. So for the transmitted one, we have phi transmitted. This is going to be b e to the I p z, and not only p, but p prime actually. Then we have the derivative. So the derivative of the transmitted wave with respect to z, this is I p prime b, and the exponent will go to 0, so we get 1. Now the conjugate wave function will be, let's see, so b conjugate e to the minus I p prime conjugate z, and then we take its derivative, so d dz, and we get b conjugate minus I p prime conjugate. And times the exponent, of course, but the exponents will all go to 1 as before, so no need to worry. And then we have the transmitted, probability current, which comes simply from the formula, which again, it's the conjugate one first. Where is it? There. So it is conjugate phi, so we get, well, of course, 1 over 2 mi. Let's not forget 1 over 2 mi. And then we have b conjugate times this, so I p prime b minus, then we have b times this, so minus I p prime conjugate b conjugate. Okay, so now let's see, the i's, they will cancel out. The minus sign turns into a plus, so those ones are gone, this is gone, and we end up with p prime plus p prime conjugate divided by 2m times b conjugate. But we already know what b and b conjugate are, so let's plug them in. So p prime plus p prime conjugate over 2m. Now b, what is b? b is somewhere over here. There, 2p divided by p plus p prime. So 2p divided by p plus p prime, and b conjugate will be 2p divided by p plus p prime conjugate. So I guess we can just put these together and we have 4p squared, and I guess we can simplify the 4 with this 2 right there. So we get 2p squared. Okay, so now we have the currents, and with those we can calculate what we actually wanted, which is of course the reflection and transmission coefficient. So the reflection coefficient will be the reflected current divided by the incident one, right? So J reflected divided by J incident. So what is the reflected one? It is right here. It is P over M times P minus P prime, P plus P prime, P minus P prime conjugate divided by P plus P prime conjugate. Then we have the, and we still have to divide by the incident one, which is P over M. But P over M, they will simply cancel out. Okay, then we have the transmission coefficient, which is of course the transmitted current divided by the transmitted, the incident current. Okay, so this would be P prime plus P prime conjugate divided by M times 2P squared divided by P plus P prime times 1 over P plus P prime conjugate, and we divide all of this by P over M. So the M's will cancel out, and this P will cancel out this squared. Okay. Now, we have found like these overall expressions, but we haven't really said anything about the strength of the potential, and we don't really know what's going on with P prime, right? It can be complex sometimes, but when is that going to happen, right? When will P prime be complex? When will it be real? Let's begin discussing that. So let's go back to our expression for P prime. I don't think that we need any of this anymore, so blah, 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 blah. Or do we? I don't think, well, I hope not. Okay, actually, yeah, the lower part may be relevant, so I will keep that. Okay, so I'll stick to this part. All right, so let's try to figure out when P prime is real. So what is the condition on the interior, or actually rather this part, right? This is P prime. What is the condition on the interior, this and this, for P prime to be real? So if we want P prime to be real, we need this to be positive and this to be positive, or both to be negative. Okay, so let's go for the first condition. So for if they are both positive, that means that E minus E phi 0 plus M is greater than 0. And also at the same time, right, and E minus E phi 0 minus M is greater than 0. So both of them at the same time. So from here, I guess the simplest condition to see is, of course, E minus E phi 0 is greater than M. Because if this condition is satisfied, then this one is immediately also satisfied. Because if this is greater than M, then you add it to m, and you're always going to be positive, right? So this condition right there is sufficient for us to know that if this is satisfied, then p prime is real. So this is e minus e phi 0 greater than m. Okay, so this is the case, by the way, where we have a weak potential. Weak potential, right? It is not big enough to change this balance. And then we have another possibility, right? What if they are both negative? So in the condition for them both to be negative, we would have e minus e phi 0 plus m smaller than 0, and also e minus e phi 0 minus m smaller than 0. So from here, it's going to be easier to take a look at this expression, because if we have e minus e phi 0 smaller than minus m, that means that if this is true, then this is smaller than minus m, and then you just add minus m, and there's no way that's ever going to be positive. That's always negative. So now this is the condition that is sufficient for us to know that this condition is satisfied and that p prime is going to be real. Okay. So this is the case where the potential is strong. So this is a strong potential, right? Because the negative comes from the potential. So if the potential is very strong and it is strong enough to basically take E from positive to all the way to negative, then yeah, that's because the potential is strong, and that is that case. Then what is the condition going to be for p prime to be complex? Well, here we are simply left in the intermediate case. You can just analyze it like we just did and see that they have to be like 1 and 1, right? 1 positive, 1 negative. But you can also see that we have gone through like every possible value of m except for the intermediate place. So the condition would be that e minus e phi 0 would have to be between minus m and m. Okay, so these are our conditions for p prime to be real or for it to be complex. Okay, so now that we know that, let's go back to our coefficients right here, and let's begin finding some values. So let's just go for the weak case, right? We are going to go through them all, but let's begin with the weak potential. So weak potential. In that case, keep in mind, p prime is real. So that means that p prime is the same as p prime conjugate. So in that case, the reflection coefficient is going to be, let's see from this, if p prime and p prime conjugate are the same, then we get simply p minus p prime and p plus p prime squared. And the transmission coefficient, if they are the same, oh, I'm missing a line there. I don't know what happened to it. If p prime and p prime conjugate are the same, we get 2p prime times 2p, and then we have to divide by p plus p prime squared. Okay, so that would be that case. And now let's check that this indeed is 1. So if we add these together, we get p squared minus 2p prime p plus, and then we have p prime plus this term right there, which is 4p p prime, and we divide this by p plus p prime squared. So we can see that, right, this one will partially cancel out with this. And here we end up with p plus p prime squared divided by p plus p prime squared, and this is 1. Okay, so we can see that r plus t is indeed 1, which is what we expect. And this case is actually something that we have encountered in regular quantum mechanics. So this expression may even look familiar, right? That expression that we found is the one we usually found in such problems in quantum mechanics. Okay, so that is the first one. Now let's go further down and go for, let's say, the strong potential. So let's go for another case where p prime is real. Now let's go for the intermediate potential. So the intermediate. So in this case, we know that p prime is purely imaginary. So that means that p prime conjugate is minus p prime, right? It is purely imaginary. There is no real part, so you can see that you simply have to put a minus sign in front, right? Why do we know it? Because, well, this was the original expression. Where is it? Somewhere over here. Yes, this square root. So if this is negative, that means that you have an I, right? You would have an I, and then you simply have to put a minus sign in front if you take the complex conjugate. So that's why we know that. All right, and now we're going to do the exact same thing as before. So we're going to take our expressions for r and t, which I think I will move them because it's a little bit far away. So let's just move them somewhere to the side maybe. And now let's go ahead. So now in this case, we have that r is going to be p minus p prime, p plus p prime, and then we have p minus p prime conjugate. But we know that p prime conjugate is minus p prime, so we get p plus p prime, and we have p minus p prime conjugate. So you can see that they cancel out. Oh, sorry, conjugate, not anymore. We already used that. You can see that they cancel out, right? This and this and this and this, and we get 1 as our coefficient of reflection, which is quite interesting. Let's go now for the transmission coefficient, which is right there. And in that case, we can see right away, we have p prime minus p prime and times everything else, but this is already 0. So the entire thing is 0. So we can see that r plus t is indeed 1, even though in this case there is no transmission, which is quite interesting. Now, in the case of this strong potential, let's keep in mind, let me see where we have the condition, right here. The strong potential is the case where E minus E phi 0 is smaller than minus m, which means that E minus E phi 0 is less than 0. And the condition that we saw previously when we did the whole group velocity thing, we saw that if E minus E phi 0 is smaller than 0, then P prime is less than 0. Okay, it is negative. So what we know is that P prime is real, but P prime is negative. Okay, so keep that in mind. So that means that now if we go into this case for the strong potential, so strong potential, this means that P prime is going to be the same as P prime conjugate, but we have to be careful to note that P prime itself will be minus the absolute value of P prime. Okay, so let's use that and plug it in. So we have that the reflected coefficient will be P minus P prime, but P prime is minus the absolute value. So we get minus minus, so we get plus the absolute value of P prime. And then we divide by P plus P prime, but that is minus absolute value of P prime. And then we multiply by P minus P prime conjugate, but P prime conjugate is P prime, and P prime is minus the absolute value of P prime. So we get minus minus, which is plus. And then we have, well, it's going to be the same as here. So there we go. So this is simply P, actually, I'm just going to do it faster. This is just this thing squared, much faster. So this squared. Now for the transmission coefficient, we have, let's see, P prime, which is minus the absolute value of P prime, minus the absolute value of P prime. And then we have 2P divided by P minus the absolute value of P prime, and times the same thing. So this thing will be squared as well. Okay, so this is going to be minus, this is 2 times the absolute value of P prime, so we get minus 4 P absolute value of P prime divided by P minus P prime squared. Now this looks quite similar to what we saw in the case for the weak potential, right? We had in the case for the reflected P minus P prime divided by P plus P prime. So it is the same, but with the signs switched and the absolute values. And here it also has signs switched for P prime. And let's see what this actually is. take a look at this reflected coefficient. What is up here is always greater than what is down here. So that means that the reflected coefficient for a strong potential is greater than 1. Whoops, than 1. And look what happens in the case for the transmitted coefficient. Here we have something negative. This is positive, positive, positive. So that means that the transmission coefficient is always smaller than 0. And what happens if we add them together? If we add them together, we get p squared plus 2p p prime plus p prime squared. And all of this, well, both of them will be divided by the same thing. So I'll just keep it like this. And then we have minus 4p p prime. So notice, yeah, we can just add them together. And instead of having, this minus 4, we will have minus 2. And we will actually get 1, right? This thing up there is the same as what we have in the denominator, right? This is simply p minus the absolute value, right? This is p minus p prime squared. So we have that the probability is conserved, but we have more than 100% chance of something being reflected, right? I mean, you can have more reflected than arrived, and you can have like a negative amount transmitted, which makes no sense. From quantum mechanical point of view, this is not, what is this, right? And this is precisely what is known as the Klein Paradox. This is the Klein Paradox. Because if you use, right, the Klein-Gordon equation, you find this just crazy thing. This is unthinkable, right? How can you, like, just look at it like this. If you have our barrier, right? And you have some wave that has some amplitude, maybe it goes all the way over there, and then it continues, and then it is reflected greater than it came, and then you have like kind of like a weird negative transmitted. It makes no sense. Unless when it interacts with the electrostatic field or the electrostatic potential, you were to create a pair of particles. Maybe some would go back, some of the newly created particles would continue. That would allow you to have something like this situation, right? And when they come together, they cancel out and nothing is changed. So the Klein-Gordon equation has shown us here that this doesn't accurately describe a relativistic quantum mechanical system. And one of the reasons is because it is possible for particles to spontaneously be created when we have energy, right? Especially when it is interacting with an electromagnetic field. And that is something that we have seen in quantum mechanics a little bit as well, for example, in time-dependent perturbation theory. So in the end, having a theory that doesn't include the possibility of having particles appear continuously, it just is not complete, right? We can see that there's going to be problems, and we need a quantum theory that will account for this. And we will get there soon, right? So I hope that this was clear. In the next lecture, I will show you what the next step is towards building a theory that is not only quantum, but also relativistic and can account for this, right? That's where the notion of fields will very soon come into play. So I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.